Hi, Assalamualaikum. I hope you guys are doing good. So in this video, I will talk about energy equation, and this is in lecture 8. So if you see the contents of this lecture, there are quite a lot subtopic. However, in this video, I will review the first law of thermodynamics, and I will also do the derivation of the energy equation in the control volume, and from there we will get the steady flow energy equation to be applied to the incompressible flow in a single pipeline, and we will compare the equation with Bernoulli equation, and last but not least is by introducing the kinetic energy correction factor. And for the application or the examples, we will do in the online class, which will take place on Monday next week. All right, and the concept of hydraulic and energy grid line will be discussed or explained in a separate session. Okay, so if you still remember when you took thermodynamics course, the first law of thermodynamics, it states it is a statement of the conservation of energy. Okay, it states that the time rate or the energy stored in the system is equal to the energy addition by the heat transfer into the system plus the energy addition of the work transfer by the system. So if you see here, the delta E is the change of energy of the system, and Q is the heat transfer to the system, and W is the work done by the system. Okay. So if you write these terms in rate form, okay, you divide by time, you get rate of energy, rate of heat transfer, rate of work done. So if you write in terms of rate, okay, energy is measured in joule, while time is in second. So joule per second is basically the unit for power. Power that is denoted by P. So instead of using joule per second, it is common to use watt. Watt. So energy can be splitted into three main components, which are the kinetic energy EK, the potential energy EP, and the internal energy EU. So kinetic energy is due to the movement or the motion of the body. So in this case, it's the fluid particle. So kinetic energy can be measured by using half mv squared. So since the energy is in rate form, so mass is in rate form as well, which is the mass flow rate. So potential energy is due to the height or elevation. So in this case, the potential energy EP is mgz. So similar to kinetic energy, it is in rate form. So mass is the mass flow rate. While the internal energy EU is the energy associated with the intermolecular activities of the fluid molecules. So you can measure it by using m times small u, which is the specific internal energy. So similar to the other two components, energy components, it has to be in rate form. You put a dot. Okay. So if you still remember in lecture 6, okay, if you go back to the video, okay, I have derived the Reynolds transport equation, okay, which is the tool that is used to analyze the flowing fluid. Okay, the flow. So this is the Reynolds transport equation, which can also be called as general control volume equation. So this X is the any extensive properties. So in lecture 6, I replaced this X with mass and I got the mass conservation equation. And in lecture 7, I replaced this X with momentum and I got the force and momentum equation, or also called as linear momentum equation. So in this lecture, I will replace this X with energy. So when I replace with energy, I got this dEc over dt, which is the rate of the energy of the control volume. C stands for the control volume, equals to dEs over dt, the rate of energy of the system. Okay, S is the system, plus the summation of rate of energy at the inlet minus outlet. And as I mentioned just now, in the first law of thermodynamics, the total stored energy of the system is equal to the energy addition by heat transfer into the system plus the energy addition of the work transfer by the system. Okay, so if you write it in rate form, okay, you will get this. Okay, so this term, okay, in the Reynolds transport equation just now, okay, it will can be replaced with the heat transfer and work done. So when you replace this term with Q and W, you will get this equation. So this equation is called as the general energy equation. Okay. So from here, sometimes it is very hard to calculate lah, because normally you have to get this value Q, W. So you have to calculate it first. You have to ensure this W is shaft work or flow work, and energy. You have to split it into the three main components that I mentioned just now. So we go further. Not just the energy, the work can also be divided into two components, which is the shaft work, which is denoted by Ws, and the flow work, which is denoted by Wf. So shaft work is the work done by the shaft that is rotated in the turbo machine. For example, in a pump or turbine. So the shaft will be rotated, okay, so that it will do work. It will do work. Okay. While the flow work is the work done by the system on the surrounding due to the pressure forces. So pressure forces exist at the inlet and outlet. Therefore, the flow work is the difference of the workflow at the outlet minus inlet. Okay, so it can be measured by using M times P divided by rho. So in the rate form, it is mass flow rate times pressure and divide by density. Okay, outlet minus inlet. Okay. So if I want to include all this into the general energy equation, okay, let me write it first. So dEc over dt Q dot W dot energy in minus energy out. Okay. So Q will be remain. Okay. While W will have shaft work plus flow work. Well, the flow work is um, the difference between the outlet and inlet flow work. So shaft work will be remain here. Okay. So since I put it negative here following this. Okay. So this flow work is this flow work is flow work at the outlet minus flow work at the inlet. Okay. So minus, okay, and minus plus. Okay. So flow work at the inlet is a plus, flow work at the outlet should be a minus. Okay. So when you put it here, okay, you put it together with the energy, because energy also has inlet and outlet components. So summation of energy, you can split energy into three main components, okay, which is the energy due to the kinetic, the energy due to the potential, the energy due to the intermolecular activity or internal energy. So the flow work at the inlet is a plus here, so it becomes a plus here. Okay. So this is the inlet. So for the inlet, normally I use 1 minus. So energy at the outlet, we have kinetic flow work. So flow work at the outlet is a negative, so it's a negative here. So at the outlet, we use 2. Okay, inlet 1, outlet 2. Okay, so if you expand this, I write this again. Okay. Okay, so from here, I write this Q will be remain W S. So this one you use the equation, which is m dot, okay, m dot at the inlet. So this should be half v squared gz u, and the flow work is P divided by rho number 1, which is the inlet. While the outlet, for the outlet, you should get m dot 2 outlet, times half v squared plus gz plus u plus p over rho for the outlet. Okay, so this is the long equation for the general energy equation. So this m dot, sometimes you can use rho q or rho av. Okay, it depends on what the information is given to you. And so if you go back to the slide, so you see here, it should be similar to what I have just written. So this is the general uniform flow, okay, of energy equation. Okay, while this one is for non-uniform flow. So if you still remember, for non-uniform flow, you have to integrate in respect to the area. Okay, so but we haven't finished yet with the derivation. Okay, so if I go back to here, from here, I know that the flow is steady. Okay, pump is a steady flow device, turbine is steady flow device. So the flow must be steady flow. So when the flow is steady, okay, similar to the other mass conservation equation, the force and momentum equation, for this term, which is the rate of the, in this case is the energy, okay, of the control volume, is equal to 0 if the flow is steady. Alright, and for a steady flow, you can use one notation for the mass flow rate because mass in is equal to mass out. Okay, and then for the shaft, so we can have either the pump or a turbine. Okay, so for a pump or a turbine, okay, the work done, okay, it depends on the device lah. If it's a turbine, okay, work is done by the turbine. Okay, so work is done by the turbine. So when work is done by the turbine and work is done on the pump, so one is a positive, one is a negative lah. Okay, one is positive, one is negative because this work is done by the turbine. Okay, and this one is work is done on the pump. Okay, so if you replace into the long equation of the general energy equation, this will be 0 because it's a steady flow. So Q minus, so W shaft now becomes WT plus WP. You put it here, WT, WP. Okay, because it's a negative before this, right? Minus W shaft. Okay, and then for the mass, half V squared GZ U P over rho for the inlet, and minus M dot should be the same, half V squared plus GZ plus U plus P over rho. Alright. Alright, so if I want to rearrange this, okay, I want to rearrange this and I want to divide everything with mass flow rate, because I want to make it to be I want to make everything to be in specific form. Okay, so I rearrange this. I got Q minus WT plus WP. So rearrange, I got this M dot okay, V2 squared, the outlet minus the inlet because I put it on the other side. So the outlet will minus the inlet. U2 plus P2 divided by rho minus M dot, okay, V2 squared. Not the V2 squared, it's the inlet, so V1 squared. So minus, sorry. So minus GZ1, okay, or if you want to make it in bracket first, so this will become a plus U1 plus P1 divided by rho. Okay, so now I divide everything with the M dot, so it will become a specific form. Okay? So when you divide, sorry, this one should be in red, 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 red. Okay. So when you divide this long equation with mass flow rate, it will become a specific form. So the specific form of Q is the small q, specific form of Wt is small w, and the specific form of Wp is small w. Okay, and this will become half V2 squared Gc K minus plus plus half V1 squared. So this one, the minus, because I opened the bracket already. So GZ1 it's a minus again, sorry. U1 minus P1 over rho. Okay, so you got this. Okay, try to put the components that goes into the control volume on your left side, and try to put the components that goes out of the control volume on your right side. Okay, so this is the equation. Okay, that's the equation, and this is the mass flow rate just now. This is the work of shaft. So work done on the pump, the work done by the turbine. So it's going up, going up. So it's a minus. Okay. So the work, okay, this one is in the specific form. So try to rearrange this so that the components that goes into the control volume is on the right, on your left side. The components that goes to the out of the control volume is on the right side. So the components that goes into the control volume is the inlet kinetic term. Then we have this one. Okay, you go to the other side, it become everything here should be a positive. Okay, so positive GZ1. Okay, we leave the U first because U is the internal energy. So I take the pressure term. Okay, and I also have, if you go back, this work, one is positive, one is negative. So which one is going into the system? Go back to here. Which one? The pump or the turbine? It should be the pump. Go work done on the pump. So it's going into. So when it's going into, it's a plus. Okay. And it's equal to the velocity component at the outlet going out, the elevation component going out at the outlet, the pressure component at the outlet going out. And for the turbine, the work is done by the turbine going out also. So here should be work done by the turbine. Okay. And then, sorry, there is no dot there because it's not it's in the specific form. Okay, we divide by m dot just now, right? Okay, and here did I put, yeah, same. And remember that we have another term here, which is the U1, U2, and Q. Okay, so U1, U2, and Q, I put it together. So it become plus U2 minus U1 minus Q. Try to rearrange. Okay, U2 is a positive here on your right side. Okay, minus U1, and Q comes from the other side and it becomes negative. So I put it in the same bracket. Okay, so this equation, okay, if you see the the term in the bracket, it represents the thermal energy, okay, because when fluid flows, some mechanical energy will be changed into thermal energy through viscous action. Okay, so this is for real fluid. So this cause increase in internal energy, okay, with the temperature rise, okay, and eventually dissipated to the surrounding in terms of heat, and thus it represents loss in the system or loss in the flow. Okay, so when I rewrite this, okay, I want to rewrite this term. It will become energy loss. Okay, into okay. So all this term I call it as energy loss. Okay, EL. Okay, but this is not finished yet. We don't want to leave this equation in specific form. Okay, so the common form, okay, the common form is in head. Okay, how to get it in head? I divide everything with G. When I divide everything with G, I got B1 squared over 2G plus Z1 plus P1. So P1 rho times G, you divide by G, rho times G is basically gamma. Okay, so this is specific energy. You divide by G, you get uh, specific energy per weight. Okay, so therefore I call it it is called as head. So head supplied by the pump. Okay, so everything here should be in meter. Okay, elevation in meter. P pressure divided by gamma, you get meter. V1 square over 2G, you get meter. And this is meter. It is called head. And it's equal to V2 squared over 2G plus C2 plus P2 over gamma plus head given out by turbine. Okay, so this is the specific work done by turbine. And this energy lost is called as head loss. Head loss. Alright. So this equation is called as steady flow energy equation, okay, or SFEE. Okay, steady flow energy equation. Alright. Okay. So this is the equation. HP is the head supplied by the pump, HT is the head given out in turbine, and HL is the head loss in pipe. Okay. Alright. And the unit is in meter. Every single term here is in meter. Okay. So this is the example that we are going to do in our online class next week on Monday. Alright. Okay. So before that, before that, if you go back to the SFE equation, okay, so I write this again as FEE or steady flow energy equation. Okay, So normally, okay, in the Bernoulli equation, okay, we write pressure first, right? So I will just rearrange the SFVE so that I write P pressure first, then I write the elevation term, and I will write the velocity, kinetic term, and I also have this HP in this equation. It's equal to P2 over gamma V2 V1 over 2G HT plus HL. Okay, so I rearrange. Okay. Just now, when we derive, we got the V first and Z and P and HP. So I rearrange. So if you go back to the Bernoulli equation, okay, in the Bernoulli equation, if I write it in head, I will get this plus this plus this equals to the outlet term, right? So I should get this. So what's the difference between SFEE and VE is that we have an additional term here. Okay, so this additional term, which is the HP, HT, and HL, okay, is the difference between SFE and BE. So that's why in BE we have a few assumptions or limitations. Okay? It has to be inviscid, it has to be what? It has to be frictionless. So these are the terms that I use in the exam. Okay. I also use no work and heat transfer. Okay, so that's why you have this limitation in Bernoulli equation. Okay, because Bernoulli equation is also the statement of the conservation of energy for frictionless inviscid fluid, okay, or flow. Okay, no work and heat transfer because it doesn't involve any turbo machine. But in SFVE, okay, you either have a pump or a turbine, and you will have losses in the piping system. Alright, so that's the difference. So since we have included the viscous flow, we have included this is a real fluid, okay. So this velocity, okay, for a real fluid, if you still remember, for a real fluid, there is this condition where at the wall, the V will be 0 due to the no slip condition. Okay. So as you go far, the velocity increases, then it decreases. Okay, it's symmetrical. As you go far from the fixed wall, it increases. Velocity increases and in maximum at the center lah. Okay. Or for um, in a turbulent case, you should have a different profile here. Okay. So due to this, okay, which velocity you want to use? Okay. So if you want to have this velocity profile equation, and so most of the time it will not be given. Okay. So therefore, we have to introduce a correction factor in front of the velocity. So this correction factor is called as kinetic energy correction factor. Okay. Um, so how do we get this value? And you should have this alpha or the kinetic energy correction factor for both velocity at the inlet and outlet. Okay, so the velocity must be the average velocity. Okay, so how do we get? It is given here. If the flow is laminar, the alpha value is 2, and if the flow is turbulent, it is approximately 1. So in the most common practice, the flow will be turbulent. So therefore, alpha is normally assumed to be unity or 1. Okay? Alright. So I think that's all in this video. I see you guys later in the online class for the example. And if you have any question, you can ask during the online class. Thank you.